Hi everyone, welcome to the solid state. So as I already said you, write down these all important formulas and important points in 1 to 2 pages only. Okay, try to complete in 1 to 2 pages and read everything before the exam. Okay, let us start. So the first one is total lattice points per unit cell. This is very important, you have to remember. So we have SCC, simple cubic crystal, or we can say primitive unit cell. So next one is BCC, body centered cubic, face centered cubic, end centered cubic, edge centered cubic. In SCC we have totally 8 corners. Okay, we have totally 8 corners. I hope you people already know about this, that's why I'm just reading everything. Right, 8 corners. So every corner contribution per unit cell 1 by 8, because one corner is in between 8 unit cells, so that's why I have written like 1 by 8. So 8 into 1 by 8 contribution, 8 get cancelled, so 1. So total lattice points per unit cell in SCC, or we can say primitive unit cell, 1. Next one is BCC, body centered cubic. 8 corners are there and body centered cubic. At the body center we have 1 atom, right? At the 8 corners 8 atoms, and at the body center 1 atom. So 8 into 1 by 8, first of all, plus 1 body center. So 1 into contribution of body center is 1. So 1 into 1, 2. So totally 8 into 8 get cancelled, 1. So 1 into 1, 1. So 1 plus 1, 2. So total 2 lattice points are there in this unit cell. So next FCC, how many number of particles or how many number of lattice points are there in FCC? So totally, so everything is common. 8 corners are common in every unit cell, right? So 8 into 1 by 8 plus 6 phases. So 1 phase contribution, 1 particle in 1 phase. So the particle contribution, if you see, in between 2 phases 1 particle is there, right? 1 particle is in between 2 phases, so that's why contribution is 1 by 2. So 6 into 1 by 2, 2 3 is 6, 3 plus 1 4. So 4 particles are there in FCC. Next, end centered cubic, 8 into 1 by 8, 1 plus 2 end center. End center means top and bottom. So the particle should be located at the center of the top and bottom of the top and bottom phases. Alright, so 2, so total 2. So 2 into 1 by 2 contribution. Okay, like phases. So 1 by 2 contribution, 2 get cancelled, 1. So 1 plus 1, 2. So total 2 particles are there in end centered cubic. Next, edge centered cubic, 8 into 1 by 8, again 1 plus. So 12 here. So 12 edges. If you take the crystal system, primitive unit cell, you can see 12 edges totally. So 1 edge contribution, 1 edge is in between 4 unit cells. So 12 into 1 by 4. So 4 3 is 12. 3 plus 1 4. So totally 4 particles are there in edge centered cubic unit cell. So you have to remember this. So 1 2 4 2 4. Okay, you have to remember this numbers. Next, 7 types of crystal systems are there. So totally 7 types of crystal systems are there. 14 Bravais lattices are there. You have to remember. So in these 7 types of crystal systems, first crystal system, cubic unit cell. Okay, you know this. So cubic crystal system. So cubic crystal system length is A equal to B equal to C. You have to remember this. Angle alpha equal to beta equal to gamma, which is equal to 90 degrees. Bravais lattices, total 3 lattices are there in cubic crystal. Okay, so types of unit cell. So those 3 are, one is primitive, next body centered, next face centered cubic. Okay, so next one is rhombohedral crystal system. In rhombohedral crystal system, length is A equal to B equal to C, and angle is alpha equal to beta equal to gamma, but here not equal to 90 degrees. Here equal to 90 degrees, here not equal to 90 degrees. Bravais lattices only one, that one Bravais lattices is primitive here. Type of unit cell is primitive. Next, tetragonal system, tetragonal crystal system. Here the length is A equal to B not equal to C, and angle is alpha equal to beta equal to gamma equal to 90 degrees. If you see, alternate angles are same. Here alpha equal to beta equal to gamma equal to 90 degrees. Here also alpha equal to beta equal to gamma equal to 90 degrees. If you observe, alternate angles are same. Next, here 2 Bravais lattices are there, and here type of unit cell, primitive and body centered. Here 2, so primitive and body centered. Next one, hexagonal crystal system. So hexagonal crystal system, A equal to B not equal to C. This is the length, and angle is alpha equal to beta equal to 90 degrees, but gamma equal to 120 degrees. Okay, and Bravais lattices, only one Bravais lattice is there in hexagonal crystal system, that is primitive. Okay, next orthorhombic crystal system. Orthorhombic crystal system, length is A not equal to B not equal to C, A not equal to B not equal to C. Again, if you see, alternate angle, alpha beta gamma 90 degree. Alpha equal to beta equal to gamma 90 degree, and 4 Bravais lattices are there in this orthorhombic system. Those Bravais lattices are primitive, body centered, face centered, edge centered. Okay, these 4 Bravais lattices. Next, monoclinic. So the monoclinic crystal system, A not equal to B not equal to C, this is the length, alpha equal to gamma equal to 90 degrees, beta not equal to 90 degrees. Alpha gamma equal to 90 degrees, beta not equal to 90 degrees, and here the Bravais lattices are total 2 Bravais lattices are there in monoclinic crystal system. So those 2 Bravais lattices are primitive and edge centered, right? So triclinic system, A not equal to B not equal to C, angle is alpha not equal to beta not equal to gamma, which is not equal to 90 degrees. Last one, triclinic system is every angle is not equal to 90 degrees, alpha not equal to beta not equal to gamma equal to not equal to 90 degrees, and here the Bravais lattices are only one, that Bravais lattice is primitive. So if you count 3, 1, 2, 1, 4, 2, 1, if you count these all things, you will get 14. So total you have 14 Bravais lattices. Okay, so last important point, if you have FCC crystal, in this FCC crystal, number of octahedral voids, okay, number of octahedral voids equal to number of lattice points. For suppose if you take FCC, here 4 lattice points are there, right? 8 into 1 by 2, 8 corners, 8 into 1 by 8 contribution, 6 phases, 6 into 1 by 2 contribution. So totally you have 4 lattice points. So these 4 lattice points are nothing but 4 octahedral voids in FCC. If you want to calculate tetrahedral voids, what you have to do, 2 into number of octahedral void, that is 2 into 4, that is 8 tetrahedral voids are there in FCC. In FCC, 4 octahedral voids, 4 lattice points, and 8 tetrahedral voids are there. Okay, cubic. So again, in diamond centered cubic, 8 corners are there, 6 phases are there, and tetrahedral voids totally 8 are there. So 8 into 1 by 8 contribution corner, 6 into 1 by 2 contribution of the phase center, and 1 by 2 into tetrahedral voids. Total tetrahedral voids in FCC 8, 2 into octahedral voids, so 8. So total if you calculate 8 number of lattice points are there in diamond centered cubic. Next one, length. So edge and face diagonal, body diagonal. So length of the edge is A, length of the face diagonal is root 2A, length of the body diagonal is root 3A. Next one, relation between distance, edge length and radius, right? DAR. So if you see SCC, simple cubic crystal are primitive, the edge length A equal to distance D, that is equal to 2R. If you take the crystal lattice, right? If you take the crystal lattice, I don't have any space here to explain. See, if I take crystal lattice like this, okay, so here one atom is there, here one atom is there, so this is nothing but your distance, okay, but the distance between 2 atoms. Okay, so here this is the distance. So here, from here to here there is R, from here to here there is R, so 2R. So totally A equal to D equal to 2R for SCC are primitive. Next, body centered cubic. For body centered cubic, distance is 2R, distance equal to 2R, and edge length A equal to 4R by root 3. You can write this 4R is 2 into 2R. 2R is nothing but D, so you can write 2D by root 3 also. Okay, if you want to calculate distance, you have to modify this formula like that. Next, D equal to 2R. So A equal to 4R by root 2 for FCC, face centered cubic. 4R again 2 into 2R. 2R is nothing but D, so 2D by root 2. So if you want to calculate the distance, A equal to 2D by root 2, you have to write. Next, percentage of packing fraction. Percentage of packing fraction. So Z equal to 4/3 pi r cube. Z is nothing but number of lattice points. 4/3 pi r cube is nothing but volume of lattice point. Volume of lattice point is 4/3 pi r cube by A cube. This is volume of the unit cell. So number of lattice point, volume of lattice point, volume of unit cell, Z into 4/3 pi r cube by A cube. This is the formula to calculate the packing fraction. Percentage of packing fraction, percentage, so into 100. Okay. Next, for SCC, the packing fraction, if you calculate, if you just take the lattice points of SCC and put here 4/3 pi r cube value and A cube value of SCC, right? So you have to take this A value and you have to put here. You have to put here. So if you calculate by using this formula, for the SCC, the packing fraction, percentage of packing fraction is 52.3. You have to remember this. BCC 67.9%, FCC or HCP, hexagonal close packing or cubic close packing, 74% packing fraction. So this FCC is very effective packing. Okay, that's why it is called very effective packing. Effective packing means voids are very less, means empty space if you take in the lattice, so the empty space is very less. For suppose you take 100% lattice, right? So 100 minus 74, because 74% is packaging already, right? So remaining percent 100 minus 74 you have to take. So empty space is very less. Empty space is very less. So that's the reason why 26% empty space is there in FCC. That's the reason why FCC will be called as more efficient packing. Next one, this hexagonal close packing is nothing but AB type packing. AB type packing. Then this cubic close packing will be called as ABC type packing. Next one, density of crystal lattice. So density equal to Zm. So Z is nothing but lattice point, number of lattice point, into M, that is nothing but molar mass, by A cube, that is length of the unit cell. Here A is nothing but length of the unit cell. Here Na, Avogadro number, Zm by A cube Na. This is the density formula. Next, ionic crystal. Ionic crystals, if you have any ionic crystal like NaCl, right, CSCl, cesium plus Cl minus, Na plus Cl minus, that is nothing but ionic crystal. If you have ionic crystal, to calculate this edge length, you have to use this formula, 2 into distance between positive ion, for suppose Na plus, and negative ion Cl minus. So 2 into distance between cation and anion, you have to take this formula. Next, calculation of Miller indices. If you want to calculate the Miller indices, so they will give you one plane, one intercept. You have to take the intercept and you have to take reciprocal of that given intercept. You have to take the reciprocal of given intercept and you have to remove the fractions. Okay, you have to remove the fraction and you have to put your answer in the numeric value, right, not in fractions. So first of all, you have to take the intercept and reciprocal of second point, you have to take the reciprocal of intercept. Last one, you have to remove the fractions. Last one, angle between the planes. So the angle between the planes, cos theta equal to, they will give you two planes here, H1 K1 L1 and H2 K2 L2. So the formula is cos theta equal to H1 H2 plus K1 K2 plus L1 L2 by root over H1 square plus K1 square plus L1 square into root over H2 square plus K2 square plus L2 square. So this is the angle between the planes formula. Next, structure of ionic solids. First one, rock salt structure. Rock salt structure is nothing but NaCl, sodium chloride. So here Na plus ions cation, location is octahedral. Location of Na plus is octahedral. Location of Cl minus is FCC lattice. Okay. So here number of Na plus ions you have to calculate. So if you take this number of Na plus ions, so the location is body centered and edge centered, right? So body centered means 1 into 1. So 1 body center. So the contribution is 1 plus 12 edges. Contribution is 1 by 4. So total 1 plus 3, 4. So 4 Na plus ions are there in NaCl structure. Cl minus ions, FCC lattice, because octahedral void is nothing but body centered plus edge centered is nothing but octahedral void. Here FCC lattice, Cl minus FCC, 8 into 1 by 8 plus 6 into 1 by 2, you know this. So 4. So 4 Cl minus ions are there in NaCl structure. So totally 4 Na plus ions, 4 Cl minus ions is gives rise to 4 NaCl molecules. So total 4 NaCl molecules are there in NaCl structure, rock salt structure. So Z is equal to 4. Z equal to 4. Next, coordination number Na plus, coordination number of Na plus is 6 here. You have to, it's better to remember, right? And coordination number of Cl minus is 6. Next, CSCl, cesium chloride structure, and the location cesium plus ions. If you see, this is BCC type structure. Cesium chloride is BCC type structure, but not exactly BCC. Why? Because all atoms are not same. Here cesium atom is there, Cl atom is there. If all atoms are same, we can say BCC according to the location, but it is not complete BCC structure, it is BCC type structure. Now, this cation cesium plus is body centered location. Okay, is at the body center, and this Cl minus anion is at the corners. Okay, so cation is at the body center, so 1 into 1 contribution. So 1 Cs plus ion is there, and corners 8 into 1 by 8. So 1 Cl minus ion is there. So 1 Cs plus 1 Cl minus 1 CsCl. So Z equal to 1. That means 1 CsCl total salt is there in this structure. Okay. So next, coordination number of Cs plus, cesium plus is 8. Coordination number of Cl minus is also 8. You have to write this. Next, fluoride structure. So here fluoride structure means calcium fluoride, strontium fluoride, barium fluoride, like that. So here calcium plus 2 ions, positive ions, located in FCC. Location of this Ca plus 2 is FCC, and location of anion, location of F minus ion is tetrahedral voids. If FCC, again you know, in FCC total lattice points are 4. You know this, 6 into 1 by 2 plus 8 into 1 by 8. So 4. So this is the lattice points in FCC is 4. Tetrahedral voids, again 8 tetrahedral voids are there. In FCC 8 tetrahedral voids are there. If you see 4 Ca plus 2 ions now, 8 F minus ions because of tetrahedral. So 4 Ca plus 2 plus 8 F minus, totally 4 CaF2. So Z equal to 4. That means 4 CaF2 ions are there in fluoride structure. 4 CaF2 crystals, I can say salt is there in fluoride structure. Coordination number for Ca plus 2 ions is 8. Coordination number for fluoride is 4. Okay. So if you observe here, FCC 4 lattice points and tetrahedral 8. So just reverse. Okay. So for Ca plus 2 here 8, for F minus 4. Coordination number. Anti-fluoride structure, Na2O structure. So Na plus ions location is tetrahedral void. So total tetrahedral 8, you know this. O2 minus ions, O2 minus FCC 6 into 1 by 2 plus 8 into 1 by 8 again, so 4. Okay, so total 8 Na plus 4 O2 minus 4 Na2O molecules you will have. So Z is equal to 4. And coordination number of Na plus is 4, coordination number of O2 minus is 8. Just reverse. Here Na plus 8, here O2 minus 4, but here coordination number Na plus 4, O2 minus 8. Okay, so next is spellerite or blend structure. Example, zinc sulfide, ZnS. So Zn plus 2, cation location half of the tetrahedral voids, half into tetrahedral voids. Tetrahedral you have 8 here, so 8 into 1 by 2, so 4. So 4 Zn plus 2 ions are there. S2 minus FCC, location is face centered cubic or cubic close packed structure, and this whenever you have FCC you have 4 lattice points, 8 into 1 by 8, 6 into 1 by 2, so 4. So total here 4 Zn plus 2, 4 S2 minus, which is equal to 4 Zns. So Z is equal to 4 here. Okay, coordination number for Zn plus 2 4, coordination number of S2 minus 4 same like this. Okay, here 4, here 4. So here also coordination number for Zn plus 2 and S2 minus both are 4. Next one is if this S2 minus is in FCC lattice, then it is okay. If it is in HCP lattice, hexagonal cubic close packed structure, then the structure will be called as Ujjayi. Okay, so Zn plus 2 cation is half of the tetrahedral voids, S2 minus FCC, then spellerite or band structure. If Zn plus 2 half of the tetrahedral voids, but this S2 minus is in hexagonal close packed structure, then this will be called as Ujjayi structure. Then in that case, this lattice points or octahedral voids are 6 in this Ujjayi structure, right? Whenever your octahedral voids are 6, then tetrahedral voids 2 into octahedral voids, so 2 into 6, 12. So you have 12 tetrahedral voids. So whenever you have Ujjayi structure, you have to take 12 here. So now your cations half of the tetrahedral voids, half into 12 you have to take, so that 6. That means in this place you will get 6 instead of 4. In this place you will get HCP structure, so tetrahedral voids. Okay, so tetrahedral voids 12, octahedral voids 6, right? So this is spellerite blend structure, this is the Ujjayi structure. Last one, perovskite structure, CaTiO3, calcium plus 2 ions, titanium plus 4 ions, O minus 2 ions are there. Calcium plus 2 location is body center, so 1 into 1, 1 ion is there, 1 Ca plus 2 ion is there. Titanium plus 4 corners, so 8 into 1 by 8, 1, and O2 minus edge center, total edges are 12, so contribution is 1 by 4, so 4 3 are 12, so 3 ions are there, 3 O2 minus ions are there. So 3 O2 minus ions, 1 Ta plus 4, 1 Ca plus 2, total 5 ions are there in perovskite structure, and here Z is equal to 1. So Z is equal to 1 how? So 1 Ca plus 2 plus 1 Ta plus 4 plus 3 O2 minus will give rise to 1 CaTiO3. So Z is 1. So this is about this structure of ionic solids. Last, the distance between the two planes, right? Distance between the two planes, the direct formula A by root over h square plus k square plus l square. This is the edge length, this is the HKL values. Next, Bragg's equation n lambda equal to 2d sin theta, right? If it is a constructive interference, destructive interference, n lambda by 2 equal to 2d sin theta. That is n lambda equal to 4d sin theta. Next, selection rules. If you have SCC, simple cubic crystal, any HKL values, okay, this HKL values, any HKL values, okay, there is no specific number, any HKL values are allowed for SCC selection rules. For BCC, H plus K plus L if even. For suppose 2 plus 3 plus 4, like that, if you just add the numbers, if you get the even number, then BCC is allowed. Okay, this is the allowed selection rule. And for FCC selection rules, the allowed selection rules are either all HKL should be even or either all H comma K comma L are odd. Okay, for suppose 3, 1, 7, all are odd, so it is allowed. Otherwise 6, 2, 4, all are even, allowed. Okay. So next one is, you have to read about the Frenkel and Schottky defects. Just focus on that. I can't discuss here. Again, band theory is also important. So just give a read for that. Okay. Just read band theory and Schottky and Frenkel defects. Next one, if you have the conduction band here, valency band here, in between the conduction band and valency band, you have Fermi level, energy of the Fermi level. This is nothing but your intrinsic semiconductor. Okay. So next one, conduction band here. So near to the conduction band, if you have the donor band, then this conduction band will take electrons from this donor band. Okay, and valency band here. That means the energy difference between the conduction band and donor band is very less. That is n-type semiconductor. And the energy difference between valency band and acceptor band is very less. That is p-type semiconductor. Here valency band, here conduction band, but acceptor band is very near to valency band. This is p-type semiconductor. Next one, calculation of energy of Fermi levels. Intrinsic semiconductor energy of Fermi levels formula is this: energy of valency band plus energy of conduction band by 2 plus 3 by 4 kBT Boltzmann's constant into temperature log m. M means mass here, right? N-type semiconductor energy of Fermi level, energy of donor band, here energy of donor band plus energy of conduction band, because electrons are transferring from here to here, by 2 plus kBT by 2 log ND by NC. Log ND by NC, that is number of electrons in donor band by number of electrons in conduction band. Here for p-type semiconductor, the formula is energy of Fermi level equal to energy of acceptor band plus energy of valency band by 2, because electrons are moving from here to here, plus kBT by 2 log NV by NA, that is number of electrons in valency band over number of electrons in acceptor band. Next, intrinsic semiconductor. For intrinsic semiconductor, this energy of Fermi level is directly proportional to the temperature. If temperature increase, energy of Fermi level will increase for intrinsic semiconductor and p-type semiconductor also. So whenever temperature increase, if you take p-type semiconductor, temperature increase, so energy of Fermi level increase. That means your NV should be greater than NA. Number of electrons in valency band is greater than number of electrons are in acceptor band, because energy of Fermi level is high. So Na is less than NV. For n-type semiconductor, when temperature increase, energy of Fermi level decrease. That means energy of Fermi level is inversely proportional to the temperature. That means here ND by NC, energy of Fermi level decreases. That means ND is less than NC. So I can write NC is greater than ND. So this is about the solid state. These are the very important formulas from first page to the last page. Just try to complete, just try to write these all formulas within 1 to 2 pages. Okay, and read them before your exam. This is more than enough. Thank you so much.